Hello. Yeah, Dr. Vijay Krishna. Are you able to hear? Hello.
Yes.
Yeah, good afternoon. Yeah, Dr. Vijay Krishna is okay now?
Yes, okay, sir.
Yeah. Good afternoon, one and all. I welcome all the participants.
Please.
I welcome all the participants who are participated in this faculty development program in power switching converters for the renewable energy sources and fuel cell technology. This is a great program. In fact, the latest technology which was selected by our head of the department, Dr. Ramadev Madam and his team, Dr. Vijay Krishna and Anil Kumar, conducting the FDP program for enhancing the knowledge of the scientists and researchers and faculty across the country. So I request all the participants to use this opportunity to enhance the knowledge. As you know, e-vehicles are the most demanding field now across the globe, especially in America. Tesla is doing a lot of business with the e-vehicles, and it is going to spread, I think, in near future in Asia and Europe. So there are a lot of automobile companies doing research on this, and I expect all the participants to utilize this opportunity to enhance their knowledge in the fuel cell technology for the benefit of the students as well as the researchers and academicians. And as you know, we have all the eminent speakers from the top institution in the country like IITs, NITs, and CSIR research institutes, a top institute in the country, and also from the industry experts. So I congratulate all the people who are participating in this, and I welcome to this a great program, faculty development program on this latest technology. Last one decade, the fuel cell technology is the Boom Energy is Bloom Energy, a company in US. They are using the fuel cell technology and doing a lot of business in the generators. So there will be a lot of demand for this, and there are many companies who are doing the research, but after last one decade, there is no further progress and no commercial outcome has come out from the fuel cell technology. I hope this FDP will give a lot of enhancement in the knowledge for the people who are doing research and also the faculty who can really improve upon their skills and share with the students. So I congratulate once again one and all. And I thank you for all the eminent speakers who accepted to share their knowledge. And once again, thank you very much. Wish you all the best. Thank you.
Yes, sir. Thank you very much, sir. Thank you. As on behalf of students, and staff, and management of Bapatla Engineering College, a heartily welcome to all the participants and resource person and today's resource person, Dr. K. Srinivas Bhaskar garu. My heartily welcome to the session, sir. Sir Srinivas Bhaskar, sir. Hello. Sir Srinivas Bhaskar, sir.
Hello.
Yeah, sir.
Yeah, thank you, Vijay Krishna.
Are you hear me, sir?
No, I can hear you. Please, I was just put the mic on mute mode. That's why I just removed. Thank you.
Yes, give me 5 minutes, sir. Just briefly, I read out that, and then I will get back to you, sir. Surely.
Okay.
Yeah. Thank you very much, sir. Yes. Good evening, one and all. On behalf of the students and staff and management of Bapatla Engineering College, I heartily welcome for all the 5-day online FTP program on technical advances in power switching converters for renewable energy sources and fuel cell technologies for e-vehicles. So I extend a warm welcome to Dr. K. Srinivas Bhaskar garu as today's resource person, and I thankful thankful, sir, because really accepted me for invitation and regarding this our college, and it's a great privilege to our institution, sir, because we have this kind of sources to share this knowledge type of sources, and then this is a great platform to share our knowledges to others. So really, sir, hats off to you to accept me our invitation. On behalf of this, I cordially is saying one thing. This research persons, Dr. K. Srinivas Bhaskar Garu, is one of our alumni. It's really a great privilege to our college. He's doing his postdoctoral fellowship also, and really it's a great privilege, sir. We greatly this represents the brand of Bapatla Engineering College. Thank you, sir. Thank you, and once again. And then one more bit, small introduction and small instructions to all the participants. So please, these are the small instructions from the participants, and then all the participants, please go through that instructions. What I have read here. So first one, this FTP schedule for 5 days from June 1st to 5th, 2020, and the timings will be 4 p.m. to 6 p.m. So there are major two platforms. One is Zoom and another one is YouTube Live, which we are going to use for the FD for this FDP. The participants in the Zoom are very limited, and whereas in YouTube are we can accommodate more number of people. So so all the participants try to utilize that YouTube Live, so we can make them easy to participate in the FDP program. And coming for the next one, for the end of the session every day, we're having a feedback session. So kindly all the participants need to fill the feedback session on our comment or chat boxes in you both YouTube or in Zoom, or as well as Telegram app also. I request all the participants type their questions in chat or comment boxes itself. Okay, we will look it on the what are the questions which we are typing, and we will convey the same to the resource persons. But don't interrupt the session while the session is in progress. I request once again. I request all the participants try to avoid the greeting messages like that, good evening and good morning, friends, and any other greeting messages. Please try to avoid that. Why so? Because we may miss some important questions what they are posted in that chat box. So please try to avoid that greeting messages and all the messages, and try to impose whatever the knowledge shared questions. And, how many questions if you want to ask means you can write it in chat box, or and then means whatever maybe the boxes available in that YouTube as well as Zoom. And then one more, we want to make sure that each and every participant should get a e-certificate on the successful completion of this FTP. While at the same time, the person who is able to get the certificate, he has to fill the feedback form for every day as well as the attendance form. Then make sure that he is able to get the certificate at final end of the session. So, and if the participants are facing any technical problem regarding it may be an error of a link, or it may be a feedback link problem, or it may be any registration link problem, or it may be live problem. So you make sure that if you feel free to contact our program coordinators, me and Mr. Anil, and then technical coordinator Mr. Manikumar is available. So at any cost of time or any time of at a point of time, please feel free to contact, or it may be post a comment on Telegram group also. We will look it on that, no problem. So we want to inform you that the whole session is recorded, and we will upload the daily sessions on our YouTube channel. So because why? Because some of the persons, if they missed in live sessions, so they are able to get back again their sessions back again. So we need to provide one provision for that. Please, I request all the participants, please subscribe our YouTube channel. Then you can directly get the notifications from our end, whatever the maybe live will be created, and then you will directly get the notifications, and then automatically the session will be on progress. So whatever maybe the if somebody is missing the session for this day, so we will provide all the recorded videos in YouTube. So everybody, if you want listen again, if you want to read back again, or if you want to go through the session again, you can go to our YouTube channel and see that old it means past sessions also, no problem. Okay. And then from this I want to conclude that these are the main important instructions. So please try to cooperate with us and make sure that we are a great achievement from this point. So because this end, I conclude that one because my madam, this is a time to speak our HOD madam. I will invite our HOD madam also. Anil, 1 second. Anil. Hello. Anil sir. Madam.
Hello.
Madam. Matlan, madam. Please can you share your words, madam?
Okay. Honorable Secretary of Bapatla Education Society, respected principal, my dear colleagues, faculty participants and student participants, a very good afternoon to one and all. So on behalf of EEE Department of Bapatla Engineering College, a very hearty welcome to all of you on a 5-day faculty development program on technical advancement in power switching converters for renewable energy sources and fuel cell technology for e-vehicles. So I can say proudly that this online workshop is a great opportunity to all of us for facing the future challenging technical world. So I am very happy to say these words, and also I am very happy for inviting our alumni as one of the speaker. So Dr. Srinivas, Bhaskar, Karanki. Actually, we are planning for 5 days. These 5 days, each day we are scheduled as a 1 hour duration for each session. So I think this is very useful for all of us to gain knowledge in the present technology. So we are all aware that today's speaker is the alumni of our institute. We feel very great and proud because he is the one of the student of our department. So he did BTech from the Bapatla Engineering College. So afterward, he obtained his PhD from the IIT Madras. So you think that after BTech, so he did his PhD directly. So you all of us are aware that he is a very talented person. So in the session itself, you know what is their knowledge, his knowledge. So through his knowledge, all of us achieve the technical world challenging things. So moving to the highlights of our departments, actually everyone is aware that through the website, what is the status of our department in the Bapatla Engineering College. So even though a little bit explained to our department was established in the year 1995 and now offering 3 courses, diploma with intake of 60, BTech with intake of 120, MTech with an intake of 80. The department has accredited by NBA 3 times. The total number of employees in the department is 39. Out of that, 32 are the faculty members. So out of this 32 members, 7 members are doctorates, 21 members are pursuing their PhDs. So currently, department has 10 exclusive lab facilities with the state-of-art equipment. So the major equipment includes the various laboratories, power network analyzer, DSP based drives, cable fault locator, thermal image camera, numerical overcurrent and earth fault relay, 3 kilowatt solar wind plant, numerical relay test kit, and lab volt electromechanical training kit. So this is a special equipment. In that equipment, we dismantle the mission and again we put the mission as its function. So coming to the softwares available in the department is PSCAD, ETAP, MATLAB, PSIM, LabVIEW, and MyPower. From the past 3 years, our faculty are published 20 plus papers in UGC, Scopus, and SCI based journals. Department is also involved in the college level electrical maintenance, UPS work, and solar plant maintenance. So the students' point of view, the students is or achieved so many prizes in the level of state and national level. 100 plus students are placed in the campus recruitment during the last academic year. So this is the brief review of our department. I hope that all the 5-day sessions will lighten your career. Thank you for giving this opportunity. Thank you very much.
Yes, thank you, madam. Thank you very much for enlightening our department. And then we will promise you on the behalf of our department, it's really we will show that strengthen our department also. And coming to that, a small summary of the registrations from our technical department and right now we are receiving 2,700 plus student means participants registrations till now. And the most important thing is that in 2,700 participants, 17 participants are in different countries. These are from international participants, whereas countries like London, Oman, and Tanjung, and Turkey, and Indonesia, and Canada, and USA. This is really a great achievement because it shows that the brand of Babatla Engineering College and what's the resource persons we have. So that's the courage of the resource persons also. And that the most of the participants are from mostly from 17 NITs participants are registered so far, and then 7 IITs participants are registered so far. It's really very grateful because of this complete credit goes to our Babatla Engineering College EEE department and our faculty members and HOD madam and our means and resource persons of our FTP program. And coming to this session, we will conclude this one and hand over to Dr. Srinivas Bhaskar, sir. Please carry out the session, sir. Please, sir.
Yeah, thank you, Vijay.
Yeah, thank you, sir.
Can you help give me permission to share the screen?
Sure, sir. Sure, sir. 1 second. 1 second. Sir, are you getting, sir?
Let me check it. Yeah.
Yeah, thank you. Thank you. So with your permission, I want to read out your profile, sir.
Yeah, please.
Yeah, thank you. Dr. Srinivas Bhaskar received a BTech degree in from Babatla Engineering College in 2007, and he received his master degree in IIT Madras in 2019, and he received his PhD degree in IIT Madras Chennai in 2012. And after that, 2012, he worked as a 2 years for the postdoctoral fellowship, and more than 2 crores of funding projects he received that, and most of them are undergoing, and some of the projects are also completed. So, and briefly go through that some of the projects of research projects. First one, design and implementation of high-speed, low-power embedded signal processor based on custom power devices for PQ improvement. That is that 32.99 lakhs for the year of for 3 years in Jan 2017, and UK India Clean Energy Research Institute WP4. And role institute lead PI and a distinct grant and a 54.73 lakhs, 7.3 lakhs status, ongoing projects of 4 years. And third one, design and development of affordable movable solar photovoltaic water pumping system. The worth will be around 80 lakhs, 80.58 lakhs. And one more, brushless DC machine based on solar pumping system. So this worth of the project will be around 66.24 lakhs. And fifth one, power quality enhancement and control distributed generation in grid interactive system. So the worth will be around 10 lakhs. And grid-tied multi-level photovoltaic inverter with batteries power balancing system. So it will be ongoing. It's more than 2 crores of the projects. It's now will be some of the projects will be ongoing and some will be already completed. So thank you, sir. Thank you for our achievement. And also he published more than 20 international and national journals. Most of them will be IEEE and elsewhere, and some of them Springers also. So it's really grateful, sir. We have a most courageous your career, and then we wish good luck for you, sir. Thank you for the session. Please hand over, sir.
Yeah. Thank you, Vijay Krishna. Thank you.
Thank you.
Yeah, we can start, or should we wait till?
No, sir. We can start, sir. No problem.
We can start. Okay.
Madam, start checha, madam. Okay, sir.
Okay. You are able to see the screen.
Yes, sir.
Yes, sir.
Yeah. Okay. Thank you. Yeah. First of all, thank you to all the people who are organizing this particular FDP program, and it is always very much heartening for us to come back to our alma mater and deliver a lecture. I think this is the second time I'm doing it. Yeah, second time or the third time. I'm always happy to do that. And in this particular lockdown period, it is also good that you people are organizing such events which are beneficial to all the people across the world. Yeah. Okay. To start with, before going into it, I should say something about our college, which was the basic stepping stone from what I am today. The whole college environment, we are very fortunate to have very good professors at that time, including Gafur sir, then Murthy sir, as well as Ramadevi madam and Ramesh sir, many Karthik sir. Many people are, I hope they are still working there, and I had a constant touch with them. Let me try to brief you on power switching converters. I have seen the other speaker also. After seeing them only, I prepared this particular PPT. Some of them things are basic because there are a lot of participants are there. So in order to start with from the basics, then I'll go and discuss with you the recent research work we are carrying out here. So if you have any doubt, you can definitely ask me in the middle, or you can, as Vijay Krishna told, you can put it in the comment box also. I'm happy to answer them. Okay. Today's topic will be on power switching converters. And yeah, this is anyhow, as I've been working as an assistant professor in IIT Bhubaneswar from June 2014. Before that, I was in Ryerson University, Toronto, Canada, where I have basically worked on DC-DC converters for battery energy storage systems, and also on optimal battery energy storage design in distributed network. These particular topics were especially for Toronto Hydro, which is a distribution company in Toronto, Canada. And I actually joined as a Master of Science student in IIT Madras in 2007 after the passing out from Bapatla. Then in 2009, I have converted my master's into PhD in the area. I worked in the area of power electronics application to power systems, especially focusing on custom power devices. We have developed a 3-phase unified power quality conditioner in the as a part of my PhD work. And currently my research work comprises of both power quality as well as power electronic applications to power systems. We are also designing high gain DC-DC converters for renewable energy integration. Also, we are focusing on low power application, switched capacitor based low power application, which I will be discussing in this particular lecture. Okay. So the outline of the topics for today's lecture is, we will be talking on DC-DC converters. We will see the journey of DC-DC converters, right from the how it all started, right from the linear converters, what are the advantages or disadvantages, then what are the basic switching converters, then why we should move on to resonant converters, that is soft switching converters. Then we'll also talk about transphased switching converters. Then we will take up two specific research related work, which is on bidirectional dual active bridge converter for battery interface. Not only battery interface, it is for battery and supercapacitor both. And then we will also talk about switched capacitor based high gain DC-DC converter. These are the topics which we are going to cover. Hoping that most of the participants, they know the fundamentals. If you have any doubt, you can stop me at any point of time. Okay. To start with, as you know, the definition, if you talk about a DC-DC converter, it is very simple. The idea is it is converting the, hello, are you able to hear me?
Audible.
Yeah, okay. Yeah, basically the converting the unregulated DC input to a controlled DC output with a desired voltage level. This is pretty straightforward. There is a lot of, for example, you take a PV panel. The output of a PV panel varies with respect to the available illumination. Then, but generally we require a load, let us take in India, we require around 230 volts, 50 hertz. Further, for the input to the inverter, you should give a constant DC or maintain the voltage at constant DC. So from a variable input, like a DC supply, you need to convert it to a constant DC output. That is the idea of a DC-DC converter. For example, the DC supply input can be from a rectifier, from a filter, from a battery, or any fuel cell. Fuel cells or any renewable energy source, for the matter of the fact. So the applications also, you all know, that is switched mode power supplies. We have DC motor control also. We'll be using DC-DC converters, battery chargers. All these things are the major applications where you use the DC-DC converter. Let us start with the very fundamental DC-DC converters, that is linear converters. If you talk about the linear converters, what do you mean by linear? What is the idea of linear converters means? Okay, you have two types of linear converters. One is series and shunt. The idea of linear converters here is the elements used in this particular network, in this particular circuit, all are linear. You take a resistor, you take an inductor, you take a capacitor. All these are linear elements. Even a voltage source is a linear element. If you take a transistor, which is used in this figure 2, for example, series voltage regulator, you may know that the transistor will be operating in 3 operating regions. In one of the region, it is called linear region. You have active region, linear region, and you have the saturation region. Okay, when the transistor is been operated in the linear region, generally we will be operating this particular transistor here in the linear region. So this entire circuit is called linear. What is the idea here is, if you see, it is basically a variable resistor. The transistor is just acting as a variable resistor there. If there is a 5 volts here and you want only 2 volts output, then you drop the remaining 3 volts across your transistor. The same thing can be done using a shunt voltage regulator also. You can see the output voltages, how they are related. The first equation relates to the series voltage regulator, that is V out equivalent to V reference into 1 plus R1 by R2. R1 by R2, that is basically a potential divider circuit. If you want a specified reference, then you can generate it by changing the reference value. Okay, the same thing we can do it in the shunt also. But what is the problem with this one? The major problem is when you have a current more than 5 amperes, there will be a huge loss in this particular transistors, or the power handling capabilities are very less in case of a linear network, linear DC-DC converters. Okay, so so we need to look after other alternatives which are available. The problem here is, once if it is more than 5 amperes, let us assume that a 5 amperes a load has been connected, it is drawing 5 amperes, and you want an output voltage to be 3 volts from a 5 volts thing. That means remaining 2 volts should be dropped across your transistor. That means 2 into 5 amperes, 10 watt is the power loss. So out to transfer a power of 30 watts or 15 watts, you are incurring a power loss of 10 watt. That the efficiency is very less. So the problem here is the efficiency of the linear DC-DC converters will be very less, but these things are still being used in some of the circuits where the current ratings are very less. Now, in order to avoid this one, we have another thing called switched power converters. One second, I'm not able to see. Vijay Krishna, hello.
Sir, speaking, sir.
Vijay Krishna, there is
Chapman, sir.
constantly I am getting notifications saying that people are waiting to join.
Okay. Sir, most of them are maximum. We are suggested to join in YouTube, sir, but they are frequently trying in Zoom, sir. No
Okay.
problem, sir. Carry on,
Okay,
sir. No
okay.
problem, sir.
Okay, but it is actually blocking my screen. That is the problem.
Oh, okay, okay, sir. Sorry, sir. Sorry for the interruption.
Okay, anyway, okay, do it. So now we'll discuss about the second level, that is switching converters. In case of switching converters, what will happen is we will not operate the transistor. You can see here in the figure 3 where you have an voltage source, then in series we have a connection made with a transistor, then the resistor. Now how this will work is, this will not work in the linear region. Instead it will work in on state or off state. When the switch is closed, it is operating in the saturation region. When the switch is open, it is operating in the cutoff region. So what is the advantage is, when the switch is closed, the resistance offered to the circuit is very less. So you can see here, the V output voltage waveform will be input voltage for when the switch is on. It will be 0 when the switch is off. Like this you can control. That means the average of the V out will be the one which is been seen by the load. Okay. So what is the advantage? Power is 100% transferred from source to load, but there is one disadvantage. The power loss will be there still in the switch. And this one also, the load will be getting a pulsating DC. It will not get a constant DC. It will get plus V in for some time, again 0 for some time. Of course, the frequency, if you increase, it can, the load may not observe that pulsating, but still you have the difficulty here. Okay. Next, in order to overcome this particular thing, and another important observation we need to make in the switching converters is, for example, instead of an RL load, if you assume that you have, instead of an resistive load, if you assume that you have an RL load, what will happen is, whenever the switch is closed, there will be a current flowing in the inductor and resistance. And if the switch is opened at given during the turn off period, there will be energy stored in the inductor, and that energy has to be dissipated somewhere. Okay, because inductor is basically, it can, when the switch is on, there is an energy stored, half Li square in the inductor. That energy has to be dissipated. If there is no path provided for that inductor to dissipate the energy, the entire energy will be dropped across the transistor or the switch we are using. So this will damage the switch. So in order to avoid that one, the next level things are, we have a basic switching converter with RL load. The idea here is, instead of only one switch S1 in the earlier converters, we are placing one more switch which is called S2. What will happen here is, let us assume that when the switch S1 is on, the inductor will be charging, store the energy, and it will go give it to the load, RL load. That is basically, when the switch S1 is open, we will turn on the S2 such that the output voltage will be shorted. That means the output voltage is 0, but inductor has a path to dissipate its energy into its resistance. Okay, in this way you can the switch from damage. But of course, we need to use two switches here. This, okay. Now, before going into the further switching converters, we need to have two basic principles of converter analysis. One is volt second balance on the inductor, another is charge second balance on the capacitor. Now, still, if you see in the previous, this particular converter, we have solved one problem. The problem is saving the switch from excess energy dissipation when the inductor is present. But there's one more problem is still available. That is, your output voltage is still pulsating. Okay, how do you solve this one? That we will be learning in few slides from now. But before going on to that, we have two important laws that need to be understood before going to the steady state converters. One is voltage second balance. The volt second balance is basically a, what does it mean is the integral of the voltage across the inductor along a switching period must be 0 for a steady state. That means once the converter goes into the steady state, whatever voltage that has been across the inductor, the average of the voltage across the integral of the voltage across the inductor should be 0. That means area, if you draw the curve of a voltage waveform across the inductor over one switching period, if you take the area under that particular curve, it should be 0. In other terms, integral is nothing but area under the curve. What I mean to say is, when you take the voltage across an across an inductor and draw the waveform, and if you take the area under that particular curve over one times switching period, then if that is, it should be equivalent to 0. Similarly, charge second balance on the capacitor means the integral of the current flowing through the capacitor along a switching period must be 0, which is analogous to inductor. Here in case of a capacitor, the current that is flowing inside the capacitor should be 0 over one switching period. These are the two basic laws which need to be obeyed during the operation of the switching converters in steady state. Now, in order to avoid the problem of having a pulsated DC output using a basic switching converters, now we will go and see in case of a buck converter. The typical diagram of the buck converter is here. Why are we using this extra inductor and capacitor? That is the, what is the reason? The major reason for this one is in order to make the output voltage free from any ripple, reduce the ripple. Okay, how do you reduce the ripple? For example, see, when the switch S is closed, the inductor will be getting charged, or the inductor will be storing the energy in half Li square. And now when the switch S is open, the inductor will now act as a source. That is called inductive quick. You can see in mode 1 and mode 2, if you observe the voltage across the inductor, that is plus and minus in case of mode 1. Once in case of mode 2, when the inductor stored energy is being dissipated into the load, then it has become the inductor itself has become a source here. This is called inductive kick of the buck converter. Then you need to also know the design of the inductor will depend whether you want to operate your buck converter in continuous conduction mode or in discontinuous conduction mode. There will be a term called critical inductance. I'll explain you when the converter will be in continuous conduction mode first. If you see the waveform, I'll go to the next wave. You all know the input to output relationship is D. The input to output is D, and the ripple inside the buck converter depends upon the duty cycle as well as the design value of the inductor, capacitor, and at what switching frequency you are turning on and turning off the switch. You can see in the second equation, delta V0 by V0 is equivalent to minus D by 8 LC F square, where F is the switching frequency. So you can choose inductor and capacitor in such a way that the output ripple can be reduced. So when you want to design a buck converter, the first thing you should know is you should predefine what is the ripple I want the output voltage and what is the output voltage I want. Those are two things. And then you can design, if you choose a switch, then you can, based on data sheet, you can tell this switch can operate at this particular frequency. So you are using that particular frequency switch, then you can find L and C values accordingly. Now, in the first form, if you see the current in the inductor, if you observe, it is continuous in nature. That means when the next first IG means the pulse which are giving to the switch. When it is on, the inductor current is increasing because it is charging. When it is off, the inductor current is decreasing. The slope is negative. When you see, when the next switching cycle started, when it is trying to turn on, then again the current is increasing from that value. That means the I minimum is not equivalent to 0 in case of continuous conduction mode, whereas I minimum is equivalent to 0 in case of discontinuous conduction mode, which is there in the next waveform. You can observe. Okay. Yeah. Let me go to the next slide. Okay. Similarly, we have boost converter. You all know the boost converter is basically used for stepping up of the voltage. Very much similar to your buck converter. Here, when the switch S is closed, inductor will be getting charged. When the switch is S is open, both inductor and the source will act as a source now. Your voltage source as well as inductor will be acting as a voltage source. And I think you can see here also inductive quick will happen, but I think I have write it wrongly. In the mode 1, if the voltage is positive and negative, in the mode 2 it will be negative and positive. So voltage source and inductor will add together and it will boost the output voltage. Again, here the capacitor is also used for observing the ripples. These are the typical voltage waveform across the inductor. That's what I'm talking about. If you take the area under the curve of VL, that is V in into DTS into V minus V out into DTS.
1 hour 5 days.
I request Vijay Krishna. Vijay Krishna. Hello. Okay. Hello. Can you hear me?
Yes, sir, we can hear you.
Okay. Yeah. When you take the boost converter, the input to output relation is 1 by 1 minus D, where you can see as the duty cycle start increasing, your output voltage will increase because the denominator is getting decreased. Okay. Similar thing, you have a buck boost converter. I will slightly go these things you all know. In case of the buck boost converter, all the same thing will happen. You can have boosting operation as well as bucking operation with only one converter. The V naught by V in is D by 1 minus D in this case. But the important thing is, in case of discontinuous conduction mode, as I said already, if you see the voltage current through the inductor, in case of a buck converter, you can see before that even the next switching start, the current has become 0. That is in delta 1 TS time itself, current has been become 0. The inductor is very small, less than your critical inductance. That's why it has discharged quickly. The amount of energy stored in the inductor is very less. So the current will come back to 0 very quickly. And during delta 2 TS time, after delta 2 TS time, the next switching has started and again the inductor is getting increased. For this one, if you see the voltage across the inductor and find out V naught by V in, which will not be equivalent to D, whereas in case of continuous conduction mode, your V naught by V in is equivalent to D, whereas in case of a discontinuous conduction mode, your V naught by V in is equivalent to D by D plus delta 1, where delta 1 is the time duration which it took from the peak value of inductor current to 0. It is represented here as delta 1 into TS is the time period, the total time period. Here D by D plus delta 1. So the advantage of running a converter in discontinuous conduction mode is, first thing is the inductor value is less. That means the size of the inductor is less, and with the same amount of duty cycle. For example, please listen carefully. If you want an output voltage of 10 volts and your input voltage is, let us take 20 volts, then what is the duty cycle you want in case of a normal continuous conduction buck converter? It will be half, because your input is 20 volts, you want an output of 10 volts. If the duty cycle is 0.5, then you will get an output voltage of 10 volts. Now let us see, if I maintain the same duty cycle as 0.5, that means half. In case of a continuous conduction mode, your output voltage will be greater than 10. How means? You just see in this formula, V0 by Vin is equivalent to D by D plus delta 1, where D is 0.5 divided by 0.5 plus delta 1. And delta 1 will be always, the total, if you take it as 1, delta 1 will be always less than 0.5. If the duty, if you take D is 0.5, delta 1 will be always less than 0.5. From the waveform you can understand. That means the denominator is always less than 1. Numerator 0.5 divided by denominator less than 1 definitely ensure you to get a higher output voltage. So what I'm trying to say is, if you use a converter in discontinuous conduction mode with the same amount of duty cycle, you can get a higher output voltage. The advantage of this one is, that means you are turning on the switch for a lesser amount of time, which will reduce the power losses in the switching converter. So in most of the DC-DC converter applications, generally they design it in discontinuous conduction mode such that it has an advantage. Both the weight of the converter will be less, as well as the power losses are also less. But there are a disadvantage, because the inductor current is discontinuous. You will have an input issue from the source. You will have an input issue. Then you need to input filtering issues. So you need to put an extra filter in the input side also. That disadvantage is there. The same scenario can be observed for boost converter in discontinuous mode. These things are being placed here. Yeah. Just to see if anyone has a doubt, you can ask me now. There are some. Yeah, there are 25. We'll spend 2 minutes. Vijay Krishna, if you have any doubt, they can ask me. Otherwise, we'll go to the next.
Sir, you can go ahead, sir. At the end of session, we will go question and answer.
Okay,
session,
okay. As of now, in the chat also, there is no question. I
okay,
hope
sir. Okay.
you are able to understand. So,
Yes, sir.
is we can operate the switching converters in continuous conduction mode and discontinuous conduction mode. It depends upon the value of the inductor you choose. That is called critical inductance will be there. If it is greater than, if L is greater than critical inductance, it will go into continuous conduction mode. If it is less than critical inductance, it will go into the discontinuous conduction mode. Each modes have its own advantage and disadvantage. That's what we explained till now. Now, next, let us go to the next one. Chook converter. Of course, chook converter is right now is an absolute one. We'll not go in details of this one, but chook converter is also similar to your buck boost converter. Only thing is that the output it is more efficient than the conventional buck converter, and the input and output currents are continuous. The one advantage is the input and output currents. That means especially IL1, because the inductor is present, this current drawn from the source will be continuous. Similarly, on the load end also, the current will be continuous. You need not have an extra EMI filters. It reduces the EMI problem. But if you run a buck boost converter or any other converter in discontinuous conduction mode, you will have the EMI issues that can be removed from here. But still, the energy transfer mechanism here is through capacitor. Whereas in case of the buck boost or boost converters, it is through an inductor. Whereas here capacitor is used for the energy transfer. Now, this is an important thing. We will talk about hard switching DC converter. Whatever we have talked now is a hard switching DC converter. The thing is that the major thrust in switching converters, the research is going on, is you want a higher power packing density. High power packing density, high conversion efficiency. These are the two things. So switching frequency, if you increase the switching frequency, definitely you can reduce the size and weight. The reason is, I'll just go back and show you one particular equation. If you see here, delta V0 by V out is equivalent to 1 minus D by 8 LCF square. Let us assume that if you have a very high switching frequency, then you can choose the inductor and capacitor values very low. Still, you can achieve a very good ripple out, very good low ripple in the output. Am I right? If any of these three quantities should be high, such that either inductor or capacitor or frequency should be high. If the frequency is high, definitely it is a square. It is inversely proportional. The ripple is inversely proportional to the square. So you will have more advantage. Even in the buck boost converter also, the output ripple is inversely proportional to frequency. So what will happen is, if you increase the frequency of operation, definitely you can reduce the size of the converter, especially the inductor size and the capacitor size. But what is the difficulty if you increase the frequency? What is the next difficulty you are going to get? The next difficulty you are going to get is your switching losses will increase. If the number of switching losses will increase, especially in case of hard switching. When you are using hard switching, I'll explain you what is hard switching. But once you increase the switching frequency, the switching losses will increase, and consequently you need a higher heat sink also. So one thing you can observe in this particular diagram, during turn off time, let us assume PT is the voltage across your switch, and IT, I naught or IT is the current through the switch. You can see any switch will take a considerable amount of time. If you take a thyristor, it has 3 time intervals. During turn on process, it has 3 time interval: rise time, spread time, and hold time. T naught, T spread, all these things. Similarly, during turn off also you have gate recovery, reverse recovery, gate turn off time. All these things are there. So during that period of time, there will be an amount of voltage as well as current that is been across the switch, which is the responsible for your switching losses. During turn on it will be there, during turn off also it will be there. Of course, there will be an on-state resistance, which is a smaller value will be there depending upon what type of switch you are using. I square, I naught square into R on will also be present. These are the various switching losses as well as on-state losses. But to reduce this hard switch effect of hard switching, we can use resonant converters. These are very good attractive solutions, but also it has an associated disadvantages also, which we will be discussing now. So what is the idea of this hard switching, soft switching DC-DC converter is, it is to shape the voltage or the current waveform by creating a resonant condition. So in order to create a resonant condition, of course, we need to use one more resonant capacitor and inductor, which are much smaller than the regular resonant inductor and capacitor you are using in the DC-DC converters. Sometimes the inherent or the parasitic capacitance available in the switch itself is designed to go into resonance with an external small inductor. Okay, every switch will have a parasitic capacitance. That parasitic capacitor itself will be used, or the earlier we thought that parasitic capacitor is an will create some extra loss. But in order to take the advantage, they are now designing the converter such that that capacitor will be in resonance with an external resonant inductor and achieve the either zero voltage switching or meaning of zero voltage switching is when you force the voltage across the switch to drop to zero before it is turned on. That is called zero voltage switch. What I mean to say is, in this particular, during turn on time, you see what is happening when you want to, when the switch is in turn on and you want to in the turn off state and you want to turn on, what it is happening, the voltage across the switch is going down. It is taking some time. Instead of it falling down here, if it falls down before itself, that means ensure that the voltage across the switch is zero before you give a switching pulse. Then it will turn on with zero voltage. If the voltage across it is zero, even though the current is rising slowly, the power loss will be zero. Similarly, zero current switching means during turn off process, ensure that the current flowing in the switch is brought to zero using resonant condition and then give the pulse to turn off. The same thing is been depicted in the waveforms here. The first waveform, it shows that what is the amount of loss that you are incurring during hard switching. That means during turn on hard switching, during turn off hard switching, it has little amount of loss. Whereas in case of ZVS, during turn on, it is absolutely zero. During turn off, it has some finite value. During zero current switching, if you see, during turn off, the power loss is completely zero because the voltage, the current is made zero, then the voltage is been, then the switching pulse is been given to turn off. So okay. We can see there are various types of resonant converters. Many topology variations are there for resonant converters. The most common type are quasi-resonant converters and load resonant converters. We will extensively discuss on these things one by one. The quasi-resonant converters, they basically employ a LC tank circuit, and we can achieve zero voltage switching and zero current switching. And you have a load resonant circuits, which are basically voltage source series resonant circuits and current source shunt resonant circuits. As I explained in the previous slide, the zero current switching reduces the turn off switching losses. Zero voltage switching reduces the turn on switching losses. Out of these two, many were preferring zero voltage switching is preferable for high switching frequency. Okay. The reason is, if you see in the generally the turn on losses will be high. In case if you are able to bring the turn on losses, the zero voltage switching will enable us to bring the turn on losses to be zero. So what are the advantages means? First thing is, as I explained you earlier, the parasitic capacitance components in the switching converters can be used for generating or for achieving the resonance, and also you can reduce the switching frequency losses, which will enable us to increase the switching frequency. So once you increase the switching frequency, the size of the inductor and capacitor can be reduced. If you are able to reduce the size and the capacity, that means indirectly you are increasing the power density of the converter. At a high efficiency, you can achieve all these things. What? Just by increasing the switching frequency and you are using a resonant converter, it will ensure to operate in switching zero voltage switching or zero current switching. That means switching losses will be reduced. These are the advantages, but there are disadvantages. The important disadvantage is when you are using an inductor capacitor resonant tank, the current will definitely have a peak value. The current as well as the voltage in the switching transistor will be a peak value. That means the switch which need to be used need to be changed to accommodate this high peak resonant current. Okay, so you cannot use the same switch which you are using earlier. There should be the rating of the switch should be slightly higher. This is one problem. Second thing is regulating output frequency modulation. That means you will still find an electromagnetic interference problem in this converter. Since the current is taking a sinusoidal path rather than earlier in the hard switching, it is a normal thing. There will be excess current flowing during on state. Once the excess current is flowing during on state means extra high conduction losses will be there. That is called I square R loss. When the current increases, definitely I square R loss increases. So in the point, so you should be very careful. The total switch loss in the converter will be a combination of switching losses plus conduction losses, on state conduction losses. If you try to reduce the switching losses by employing resonant converter, but it will lead to increase the on state conduction loss. So you need to be very careful, and there should be a trade-off. When you are trying to increase the current, ensure that these resonant converters are applicable for high frequency operations. In the low frequency operations, don't put the resonant converters. You will not get any advantage. The overall losses will be still the same. Only at a very high switching frequency, you should be using the resonant converters. And another important thing is the control of this thing is slightly difficult when you want to grid integration. Okay, and that is another difficulty. Okay. Now, if you see the classification of the quasi-resonant switches, they are basically, as I told, two modes are there: current mode, zero current switching, and voltage mode, zero voltage switching. A quasi-resonant switch is nothing but a conventional semiconductor switch. It can be a MOSFET, IGBT, anything, plus a resonant tank, LC tank. So in this, there are two types, L type and N type. Again, in this L type and N type, there are full wave, half wave. In total, I can say there are 8 different types of things can be quasi-resonant switches are there. For example, ZVS, ZCS. There are two types, L type, M type. There is another types. In that L type and M type, it is full wave, half wave, and full wave and half wave in case of M type also. Let us see what is the difference. Let us take the current mode, that means ZCS. Inductor of the LC tank is connected in series with the switch. First, you take L type half wave. Why it is named L type? Inductor and capacitor are connected in such a way that it forms an L type, and there is a diode here. What is this diode is doing? The diode is allowing the current to be flowing in only one direction. Okay. And the voltage across, it is allowing the current to flow. That's why it is L type half wave. That's why it is L type half wave. When you see down, L type full wave is there, where the diode is connected in a reverse way, where if the current want to flow from left to right, it will flow in QS switch, that is switch. And if it wants to flow from right to left, it will flow in the diode. You may ask, sir, why can't QS itself will block the current to be flowing from left to right? Why an extra DS? Yes, you can even remove the DS in L type half wave. There is no need of diode there. You can remove the diode also. Still, the switch itself will allow only one way flow of the current, one direction flow of the current. Okay. Whereas in case of M type, the L and C converter are connected across the switch. The capacitor is connected across the switch and the inductor. Again, here also you have half wave and full wave. The same explanation goes. Now, in case of voltage mode, resonant capacitors are connected in parallel. See here in L type half wave, here the idea of putting a diode here is across the diode. If you see, it is called half wave. Here we are talking about the voltage across the switch. The voltage across the switch can be either positive or it will be zero. It cannot go into the negative. Okay. Similarly, you have a L type here, and L type full wave, it can allow the current flow, as well as if you see the voltage across the switch. Hello, can you hear me?
Yes, sir. Yes, sir. We are.
Yes, sir.
Yeah, totally. As I said, there will be 8 different types of resonant converters, resonant switches. Resonant switch is nothing but a conventional switch with LC tank. What type of resonant switch used depends upon your application. Okay. Let us see one example here, how we are using the resonant in this particular thing. The first wave diagram is a normal DC buck converter. Okay. The same thing in the second diagram, it is a basic converter including the losses. What are the different types of losses that can occur, especially steady state losses? The switch will have an on-state resistance. Inductor will also have an internal resistance, and the diode will be having an on-state voltage. There will be a cut-in voltage, that is VD, and then diode will also have on-state resistance, that is RD. Of course, you can put inside the capacitor also, there will be some amount of resistance. Now, the third diagram is a half wave L type. What I mean, the QS switch has been replaced with a QS, LR inductor and CR capacitor. Okay. The QS switch is just replaced with an diode, LR and CR. Similarly, in the fourth diagram, that is full wave L type, where the diode is across the switch. Okay, the current can flow in both the directions. Okay. Now let us see the operation of this one. I'll go by mode by mode. Let me show the waveforms. Yeah. Now let us see. I am discussing about the half wave as well as full wave. Let us assume when the switch QS is open and the diode is on. That is the first case. Okay. So in mode 1 is characterized by inductor charging and the storage of electrical energy in the magnetic form in the resonant inductor. Okay. In this case, QS is on. The freewheeling diode is also taking the steady state current. So what will happen is when the switch is on, this particular resonant inductor is the one which is taking the energy is being stored there, LR. And in the mode 2, what happens is if the current I0, you can see in the down T0 to T1 in this particular waveform, T0 to T1 is basically what is happening is you please observe ILR. That is the third waveform you observe. In case of third waveform, the inductor current has reached the maximum value or it is linearly varying ILR for a half wave and for a full wave. It follows the same thing. After that, it goes into the mode 2. When it will go into mode 2 means when the diode DF is been reverse biased. When the diode DF is reverse biased, it will go, the inductor and capacitor will now, please observe the second diagram in this figure. That is inductor and capacitor will now resonate. When it is resonating means the equation of the resonant, the current will be I0 plus V in by Z into sine omega t. This is the equation. When it is going into the resonance field, the equation has been given here. I0 is the inductor current is equivalent to I0 plus V in by Z sine omega t. So that particular waveform is followed here, and this mode will continue until the switch QS. When you give the switching, ask the switch to turn off, it will continue in this mode. You can see before the switch is turned off or before you are giving a pulse to turn off, what happens to the current? The current has become 0. Once the current has become 0, then you are asking the switch to turn off. That is called zero current switching. Are you able to understand? I am explaining on the figure ILR of T. When you see carefully ILR of T, which is the same current which is flowing in the switch also, because your inductor and switch are in series there. Okay. The current has become 0. After the current has become 0, you are applying a gating pulse to turn off. Okay. Gating pulse to turn off. Now the switch will be turned off. In case of L-type half wave, the current can go only to 0, but it cannot go to negative. But in case of full wave, the current in the inductor can go into the negative direction also. This is where when you have a battery on the load side, the battery can discharge or it can charge. Now, till now, whatever converters we have seen, either resonant converters, basic switching converters, or all the three types, the fundamental switching converters are your buck, boost. From these only remaining all converters have been developed. One is to step up, another is to step down. From these only remaining things are developed. But the important thing is, till now, whatever we have discussed, these converters do not have isolation between the primary, from the input and output. The ground will be common. Okay. In order to have an isolation, which is an important feature when you are dealing with an high power applications, we will be using transformized switching converters. Okay. As I said, the most important drawbacks of any basic and resonant switching converter is that their input and output are not isolated from each other. Isolation is required for isolating the common return from different parts of electronic system. So multiple outputs is required with the same voltage or different voltage. Then also we can use transformized switching converter. For example, there is an application where there is a single input, you want a multiple outputs, maybe a stepping up or stepping down. Then you can use a transformized this one. the basic transformer converters are, you have a forward converter, which is something like a buck converter only, up to a range of 100 watts to 500 watts. Then flyback converters, 5 watt to 200 watt. It is a buck boost converter. And you have a push-pull converter, which is a higher power applications are there. We'll go by one. We have an half bridge and a full bridge, which can go up to few megawatts and kilowatts also. Okay. Now, the forward converter is very much your buck converter. If you forget about this transformer and this side and see on the other side, okay, D1 and D2 are there, right? Instead of D1, if I put a switch there, is it not a buck converter? Instead of D1, forget about the transformer, everything, just replace D1 with a switch, and to that, if you give a voltage source, it is a buck converter only. But here what is happening? I am putting an extra transformer and the switch has been brought on the either side of the transformer. Now this particular thing is a unidirectional. It will allow the current only to flow in one direction. Okay. If you see, normally the V0 by Vin is equivalent to D, but in case of this particular thing, the transformer's turns ratio will come into picture. That is, V0 by Vin is equivalent to NS by NP into D. Okay, so if you see the lower voltage and the current ripple also will be reducing here, and it has a very poor transient. And the another problem with this particular thing is the transformer is utilized only half. The utilization factor transformer is only half. Okay. Now, if you see the next one, that is flyback converter, which is basically a buck boost converter, only replacing the input side with a transformer and a switch has come on this side, but the remaining structure is very much similar to your buck boost converter. In case of your buck boost converter, your V0 by Vin is D by 1 minus D. Now it will be multiplied with the transformer's turns ratio. Okay. This one has an advantage. The output inductor, there will not be any output inductor. It saves the cost and size. Okay. And you also do not require a freewheeling diode in this particular case. This many of you know, it is a full bridge converter. We will go in detail of this full bridge converter at the end of this presentation, but just to make you understand, all these transformers, please remember, these are high switching frequency transformers. These are not general transformers. For a normal transformer, if you give any DC input, it will get saturated. So you are giving a pulsating DC here. So you should ensure that these transformers are designed specifically to accommodate high frequency, as well as special core need to be used. Okay. Now here what will happen is, when switch S1 and S2 is on, you will get a plus VDC, and when switch S3 and S4 is on, you'll get minus VDC. From that, you will be getting an output voltage which is 2 times the input voltage, because on the secondary side you have a midpoint clamp midpoint transformer. This will ensure, this is also a buck converter, but it will have an output which is 2 times greater than your normal forward converter. Okay. The only difficulty here is the complex driver is complex. You need to have 4 different drivers for 4 different switches. Earlier with only 1 switch we are able to do it. Now we are doing it 4 switches. The advantage is the output is coming 2 times more, and also the transformer utilization factor is here high when compared to your forward converter, which I showed little while ago. This particular converter has only poor half utilization of the transformer, that is 50%, whereas this particular full bridge converter have a full utilization of the transformer. What I mean by utilization is, I hope you know transformer utilization factor for a midpoint capacitor and all. Please refer to that one. Having a good transformer utilization factor means it is advantageous to the DC-DC converters. Now, till now we have discussed some DC-DC converters. We'll see how these are applicable to various applications. Especially one thing is for renewable energy and battery energy storage. I will take up an dual active bridge, that is bidirectional, where you will be having a bidirectional DC-DC converter. It should have an isolated, and there are different types of bidirectional DC-DC converters. One is isolated and non-isolated. I hope you understood what is meant by an isolated and a non-isolated. Isolated means the input voltage and the output will not have the same common. They have been isolated. And for some applications, it is very important. For some power electronic based converters, it is very important. So we will be discussing about dual active bridge. The advantage of dual active bridge is it is inherently, we can achieve a zero voltage switching. Once we are able to achieve zero voltage switching, means the switching losses are less, then you can increase the switching frequency to a higher range for having a high power density converters. So what we are trying to do is, this is the basic dual active bridge converter. The idea of this dual active bridge converter is, let us assume that on the input side, you have some battery and you want to integrate this one to the grid. What will happen is, the battery, using this full bridge to the transformer, you will be getting a pulsating DC. Okay. And on the other side of the transformer, this will go. Okay. Now, the idea here is, your primary side voltage and the secondary side voltage are being phase shifted by a small angle. How do you achieve that phase shifting? The phase shifting is achieved, for example, both the sides you have a batteries. From which side to which side power has to go will be depends on how are you phase shifting the voltages. Let us assume that on the input side, on the left hand side, you have a battery with a voltage VA, and on the transformer primary, that means across the primary side, if you will be getting plus VA or 0, plus VA or 0, plus VA minus VA, depending upon how your S1 and S2 are on. Similarly, on the secondary side, you have another battery. Let us take VB. On the secondary side, based on if S5 and S6 are on, you will get plus VB, and if S7 and S8 are on, you will get minus VB, which was dissipated in this particular diagram. But you on S1 and S2 for some time, after some phase shift, you on S5 and S6. That's what has been shown here. In the first VBAT, where V primary is there S1 and S2 are on. In the second waveform, after some time, S5 and S6 are on. During the first delta time, what is happening is, the current is flowing from the primary to the secondary. It is increasing. That means the power has been transformed from the battery A to battery B. If you phase shift in this way, if you phase shift in the reverse way, the current will be flowing from battery B to battery A. Okay. So you can see here, when your in S1 and S2 are on initially, and after some time S5 and S6 are on, then only the second waveform, where it is showing you are getting high value, positive value. During this part of time, the current is increasing, and when both the switches are on, the voltage across the inductor will be very less, so the slope will be very less. During initial stage, what is the slope voltage across the inductor? It is V battery minus 0.5 times VDC. V battery minus of minus 0.5 times VDC. That means V bat plus 0.5 VDC is equivalent to this is the voltage which is applied across the inductor LR. So LdA by dt, the dA by dt will be very high. Now, when both are, all the four switches are on, that means in the primary converter S1 and S2 are on, in the secondary converter S5 and S6 are on, then the voltage applied across the primary will be V battery, and voltage applied from the second side converter will be 0.5 VDC. Both are in the positive direction. Then the voltage applied across the inductor will be V battery minus 0.5 VDC. Then the slope will be very less. Okay, this thing will keep on. It is, I have shown the steady state waveforms. So the power transfer is basically, the DAB power is being given by this particular equation. where V battery is the battery side, primary side, VDC is on the secondary side, LR is the resonant, LR is the inductor that is present here. Okay. So the power transfer can be controlled by adjusting the phase shift angle delta between V primary and V secondary. Now here I have showed a positive delta. If it is negative delta, then the power will be transferred from the right hand side to the left hand side. Using this particular concept, we have slightly modified, that is called, you have a basic cell, we have a battery here. On the secondary side, instead of using a H bridge, we have used a neutral point capacitor based switching. Okay. And after that, we have used a 3-level inverter, which is a complete grid connection. If you can see, it is a complete grid connection, and we have used ZVS operation here. So if I want the power to be going from battery storage to the grid, I will ensure that delta is positive, and then the power will be going from the battery to the grid. And if I want from the grid battery need to be charged, then I will put the delta as negative. Okay. Yeah, we have used the droop control to control the angle, the delta. If the battery is coming below the required level, then if the grid power is more, then charge the battery. If the grid needs the power, then give the power from the battery. That we have used a droop control. I'll not go into this. This is an important thing. When you want the DAB to operate in the ZVS operation, that means zero voltage operation, there are two conditions which need to be satisfied. The first one is the inductive energy stored should be enough to change the voltage across the capacitor. That means how much, and the inductor should be designed in such a way that it should be capable enough to change the voltage rail across the capacitor. But for example, the capacitor voltage should go from positive to negative using the energy stored in the inductor. This is one of the important condition for the ZVS to operate. And the second condition is the voltage transients of the resonant capacitor, that is TD, must be completed within the allotted time. The TD should be greater than or equivalent to, that means the choice of LR and CR depends upon how quickly the resonance is occurring. Your TD should be greater than or equivalent to pi/2 root over LC. Okay. And another thing is, these ZVS operations sometimes will fail if your load current is very less. If your load becomes suddenly very low, then your load current will be very less. That means the energy stored in the inductor is very less, which will not help the capacitor to change its rail. Then ZVS operation will not happen. So another important is the minimum primary current required to achieve ZVS has been given here. There should be a minimum primary current. If you cannot operate ZVS over the entire range of loading conditions. For example, if I design a particular ZVS converter which can take a maximum load of 10 amperes, then you cannot, if you are operating that particular converter in a low power range, that means if you are allowing only 2 amperes to flow, then you cannot achieve the zero voltage switching. Instead, so this is another disadvantage. You can the operative range of ZVS is limited for the resonant converters. Okay. That is what I am saying. In case of light load, the primary current flowing in the MOSFET switches are small to obtain the required dV/dt. Okay. So the resonant capacitors cannot be discharged before the switch is on. So the operation of ZVS will not occur. So narrow ZVS operation will be there. So we have done some simulation on this. Even now we are doing the experiments, but I'll show. These are the results. When P reference is like you transfer 6,000 kilowatts of power, that means you are actually charging the battery. When your P reference is positive, that means the grid wants 3,000 kilowatts, then you are actually discharging it. And you can see the battery charging and discharging in the fourth waveform, where even the current, when it become very low, when the current flowing in the primary side, the I primary is very low, even at that point of time, we are able to achieve the zero voltage switching. We have designed the inductor in such a way that even at a very light loading conditions, ZVS is occurring. Of course, anyhow, at the what I mean, how I am saying the ZVS is occurred is, if you see in the fifth figure, E figure. The dotted line is basically the voltage waveform, and this particular dark line is your switch. Okay. So when you turn on, before you turn on only, before you give the switching pulses, the voltage has become 0 because of the resonance. And then the switch is on. Okay. That will ensure your 0 voltage switching operation. Now, we'll see one more application. Basically a PV grid connected system. Vijay Krishna. Hello.
Sir, tell me, sir.
Sir, Chappan,
Do we have time to cover this one?
no problem, sir. Feel free to
Okay.
take this.
I'll just cover this one in another 10 minutes.
No problem, sir. No
Answer
problem.
session.
Matter. No
Okay.
problem, matter. Yes, sir.
So you can see here, this is a general, you have a PV array. Then normally you can put a boost converter, normal boost converter also. But if you put a normal boost converter, you need to have a lot of panels in series and parallel operation. And then you connect an inverter, then a low pass filter, then you are connecting to the grid. Now in between, here the DC link can be also be fed from a batteries. Just now I have explained the bidirectional DC-DC converter. That is the same thing again. I want to talk about this high gain boost converters. What I meant by high gain boost converter? Why I require a high gain? Why can't I use this normal boost converter? If you go back and see the relationship between the duty cycle and the V out by V in case of a conventional boost converter, it is 1 by 1 minus D. Am I right? Let us assume that I put a D is equivalent to 1. That means I turn on the switch continuously. Ideally speaking, infinity should be the V naught by V in, but that is not possible. Or if you put, let us put D is equivalent to 0.9, then V naught by V in will be how many times? 1 divided by 1 minus 0.9, that is 1 divided by 0.1, that is 10 times. So for an input voltage of 10 volts, you can get an output voltage of 100 volts. That's what the conventional DC boost converter is telling, but that will never happen. The reason is, in a practical DC-DC converter, boost converter, there are parasitic elements. Parasitic elements means an inductor which is used is not a pure inductor there. There will be some resistance. And switch which is used will have some capacitance, some on-state resistance. Taking into consideration of all these things, if you draw the exact curve, the voltage conversion ratio versus duty cycle, this is the red color is the more appropriate curve. That means after certain duty cycle, instead of increasing, the converter will fall down, or the V naught by V in will become less, or it will become 0 also. So that's why you cannot simply use a boost converter with a very high duty ratio. If you use that one, you will not get the required output. Instead, you will get the lesser output. But how do you connect a PV array? Let us you take only one PV array of 40 volts is coming from a PV cell, one particular PV 300 watts panel. Can we connect to the grid? That is a challenge. So what you should do, of course, my power levels, as I said, I want to use on a lower power level only. 300 watts machine, 300 watts converter I want to design. First, you need to step up the DC-DC converter. The reason is, if you want a 230 volts AC, at least on the inverter side, the DC link should be at least 350 volt. I'm taking a rough estimation. It's not the exact word. Generally, they say 1.6 times, approximately 1.6 times VM, where VM is 230 into root 2. That means 1.6 into 230 into root 2 will give you around 525 volts you should get. But how do you achieve from a 40 volts to 525? Then you should use high gain DC-DC converters. You cannot simply use a boost converter. I explained what is the reason. If you increase the duty cycle, definitely the voltage will fall down. So we have designed in our laboratory, which was also published in a multi-gain bidirectional switched capacitor with high efficiency and high voltage gain is proposed. The idea of this one is, this is only for applications to the low power applications. Of course, there are some converters which are being used for the high power applications also. The idea is, here it is basically an switched capacitor based. There is a V in the second if you see the power circuit, let me, this is the entire experimental setup. I'll explain you now. Let us take this V in is there here. You have a voltage which you have an input voltage. Then when the switch S1 is on, what will happen? Capacitor C1, we will be turning on switch S1, S3, S5 like that. Then what will happen is this particular voltage, whatever is there, it will charge C1 dash and C3 dash, and when the switch S1 and S3 are off and S2 and S0 are on, the energy stored in this capacitor will be transferred to the C2 dash and C4 dash. I'll show you how it is happening. Let us take this particular waveform. In the mode 1, the first version is a normal boost converter. If you see an inductor is there, a switch is there, a capacitor is there, and then another inductor, that is interfacing inductor there. It's a normal boost converter. From the normal boost converter, I am achieving a high gain DC-DC converter using the additional topology which is called a switched capacitor. So in the mode 1, what I will do is the switch is not on. So this particular voltage source will charge the capacitor CR through L in. And similarly, if you see on the other side, when diode D2 and D4 are on, what will happen? The current, whatever is there, the output from C1, D2, then C2, then LR, the current will be, so CR will be continuously charging. And in the mode 2, what will happen is, I will, after some time, D4 and D3 will go into forward bias, D2 and D4 will be reverse biased. Then whatever the energy that is stored in the capacitor will be released into the output capacitors. So in one cycle, whatever input voltage is there, the energy is stored in this CR capacitor. In another cycle, the same energy is being taken to the output. In this fashion, what will happen is the voltage across the output is a summation of all these three capacitors. That is C3. Here, the voltage across this one is a combination of the voltage across C1, 2, C3, 2, like that. Many things are there. Okay. So we have done an comparative analysis for switched capacitors. These three are the available in the literature. When compared to our proposed converter, what will happen is in our proposed converter, the number of capacitors required are only 8 and the number of switches are only required 14. Total capacitor voltage rating, which is very important when you talk about this, will lead to, this will tell us what is the switch rating you should use. In case of our converter, it is only 22 times V in, where V in is the input voltage. Okay. And there is one more parameter, also TDPR. Okay. All these things are less for our converter. Only TDPR is more in our converter, which is 12 times P in. Okay. That is the only disadvantage in our converter. Yeah, we have also done slow switching limit impedance and fast switching impedance analysis also. If somebody needs an information, I can give on this one. Yeah, to the same converter, we have put in extra capacitor and inductor to achieve the zero voltage switching also. I'll show some results on that. Yeah, this is the parameters we have chosen. We were running around 120 watts. We have designed it for 120 watts. After that, we have also designed for 300 watts also. We have gone to a frequency of 75 kilohertz. This is the whole photograph of the 120 watts laboratory prototype. That means directly you can connect a DC input and you can get the output. Here you can see what I'm trying to say is when the switch, the first waveform, and the first one VGS means it is the voltage across the switch, or when after the voltage we are achieving, you can see here the voltage across the switch is this one. When you turn off or turn on, the voltage across the switch will be 0, and then VSW is the voltage across the 0. The voltage is 0, then you are turning on. VGS is the gate to source voltage, and VSW is the voltage across the switch. The voltage across the switch is made 0, then only you are giving the gating pulse to turn on. The advantage what we got it here is, with the input voltage of 24 volts, we expected an out 5 times gain. We should be technically getting 120 volts, but we got an output voltage of 116 volts. The drop is because in each capacitor there is an internal resistance, and there are a lot of switches here. That entire thing is coming onto a loss. If you see the loss diagram as a whole, the major loss is diode losses, and since we are able to achieve 0 voltage switching, the switching losses are very less, which is only 0.62 watts, that is 11%, and the inductor losses are 13%, and you have the capacitor losses, which is 18%. In total, the amount of loss we incurred is only typically around 5 watt out of 120 watt. We are able to get out up to 116 watt this one. So this is what I can show. The efficiency is very good when compared to your normal without ZVS. With ZVS, we were able to, at 120 watt also, we are able to achieve an efficiency up to 96%. Okay. This is, now there are so many converters which are also giving 99% efficiency when they use silicon carbide. We have not used a silicon carbide. We just used an normal MOSFET. The MOSFET details has also been given here. We have used a MOSFET which is TK62N065 with 33 milliohms on state resistance. If you use a silicon carbide or an other advanced switching pattern, the losses can further be reduced. The switching losses can further be reduced. Okay. So what we are trying to say is, the ZVS operation is happened, low voltage current stresses on its components, and we can have a variable fractional voltage gain. In a normal switched capacitor, you cannot get this one, whereas the proposed one, that means this particular one, we would able to get a variable fractional gain, which is an important feature to achieve a maximum power transfer also. So when you want to use it for an MPPT algorithm, this particular converter can be used. We are doing research on that also. Yeah. So these are the other experimental prototypes. Along with that, we have also developed a 3-stage boost circuit, and then we have connected to the grid also. This is the output of a inverter, multi-level inverter. We got a very good efficiency, which is less than 8%, which is as per the IEEE 519 standards. For a low voltage grids, less than 1 kilovolt grid, 8% is still fine. Of course, it is showing 11.8% here for a 5 level, but we have also done it for a 7 level and 11 level also. In this particular way, this is shown for a 5 level. And another important thing is your input current. If you observe, it is continuous. That will reduce your EMI problems also. Even in the previous waveform also, if you can see IL in, which is a continuous waveform, once it is continuous, you will have no issues with EMI, or the EMI issues will be reduced, to be precise. Okay. Yeah, I want to stop at this point. If anyone has a doubt, they can ask me.
Yes, please, anybody you want to share something, or if you want to ask something, please you can raise your hands, or please make a question, please. Or can you post a question also, no problem. Hello.
Bananala Ratna Kumar. Yes, you are right. It is actually Carter-Wafton method only, but we have slightly modified it and put it with a boost converter in the front end, and also ZVS circuit. Your observation is correct, Ratna Kumar.
Yes, sir. Thank you.
and the complete session is recorded. It will be uploaded. And put it,
So one more question from another participant.
yeah, please.
Modular multi-level inverter real-time applications are still very less, except one or two, which are Siemens company. May I know the reason?
No, I think the modular multi-level converters are extensively used in even in HVDC applications and all. They are using it. It's not low. They're extensively using, and in future it will be much used, because once you want to integrate it to the grid, it is more required.
Okay. Thank you, sir. And one more question.
Yeah.
What are the control techniques you are using to integrate the converters to achieve good operation of the grid?
Some of my students are actually working on control techniques. They are using proportional resonant converters. The basic fundamental control they are using, but apart from that, they are using PR controller, resonant converters, proportional resonant converters, as well as comb filter based, as well as some of my students are also working on switching optimization techniques. Okay. Online switching optimization techniques, they're working on those things. Yeah.
As the participants, please, if you have any doubts, can you ask me, please?
Hello.
Yes, sir. Nobody just wait.
Hello.
Yes,
Yeah,
sir.
please.
Sir,
Yes, sir.
I am working in protection in HVDC line.
Okay.
So I am using VSC converters and MMC converters. So which one is better, sir? Actually, from your side?
See, VSI basically voltage source inverter, and this is modular multi-level converter. See, the reason why they use modular multi-level converters, can you just tell me why they use the modular multi-level converters? What is your understanding?
I think it is using protection, sir, in HVDC transmission lines. We are using protection.
Yes, one reason is protection. Any other?
I know, sir, only I have doing in protection.
See, basically, they have less dV by dt. For example, if you use an voltage source converter, they have less dV by dt. Okay. And another important thing is we need to basically achieve higher output voltage. Okay. Okay. If you want to use and also use these modular multi-converter for high power applications, you cannot use a voltage source converter. We can use, but if you want to use for a very extra in megawatt range, how do you go? So those are the reasons why you go for MMCs. Of course, I am not an expert in MMCs, but to the best of my knowledge, yes, MMCs for high power applications, they are good.
Yes, sir. One more question from Dr. Chantan Kumar. Why majorly industries are focusing on DC to DC converter topologies rather than VSI for EV applications?
No, for EV applications, see, electrical vehicle, what is your input? Either it is from the battery or you, since these are movable vehicles, you cannot continuously connect it to an AC grid. You should have an onboard grid itself. And onboard grid means it is mostly from a batteries or from the renewable energies like solar energy and all. Then the input is DC, then definitely you look after for DC-DC converters only.
Yes, sir. And one more question from Venkat Rajkumar. So what is the best optimization techniques to tune the controller of a DC to DC converter such that the efficiency of the controller may be reduced?
Maybe increased. Efficiency?
May reduce. They're asking like that.
I did not get the question. Why do someone wants to reduce the efficiency?
Yes. Maybe it may be increased.
And see, I cannot comment on what is the best optimization technique. Optimization technique depends upon what is your problem statement. Okay.
Yes,
And
sir.
these are heuristic. Some of the optimization techniques are heuristic based. Okay.
Yes, sir.
Depends a lot of the input parameters and all. So, but if in case of DC-DC converters, if you want to talk specifically in case of DC-DC converters, if you want to improve the efficiency, the thing is that you should look after the losses, especially the switching losses and conduction losses. You use a very high-end switch where the RDS on is very less, then you can use for an high power applications. Okay, let us assume that you are using an 1 megawatt, some 1 megawatt application is there. And if you say the overall efficiency of that particular system is 97%, to be precise, 97% people may think it is very good.
Yes,
But
sir.
out of 1 megawatt, 3% losses means it is in some kilowatts, which is very huge. So generally your efficiency should be something around 99% or more. Okay. So then the whole thing comes, and these are all connected systems. You have a DC-DC converter, then a DC-AC inverter. Even if one particular thing has a less efficiency, the overall system efficiency will be reduced.
Yes, sir. And one more question from Sriram Velaga. What is the maximum level up to which switched capacitor converters are recommended? What is the maximum power level?
Power level. See,
Yes, sir.
I have seen some research papers which they are using 50 kilowatt. Very recent paper in 2019, I have seen they are using up to 50 kilowatt. But we are not using so much high. The major problem is switched capacitor means the capacitor should be able to charge and discharge at the fast and then supply those power to the other side. So yeah, there are limitations with the power, but as per the literature, 50 kilowatt is there. But I recommend my personal experience, if you use it for low power switching, low power applications, they are more efficient and cost effective.
So anybody is there, or else if you want to conclude it? How can so one more question, sir? How can we model a power converter?
Model means?
It means modeling, sir. If you want to design,
you use state space model. You have a state space model where you can find out the transfer function and you can see whether the transfer function is stable or not. Then you can design a PI controller to make it stable, or feedback controllers. So most small signal modeling, average modeling is there. All these DC-DC converters we can do in small signal modeling and then find out the transfer functions, then control it. Yes.
the participants, if you want to ask any questions regarding this session, can you please ask? No problem. Or else if you want to conclude the session. Right? Yes, madam. Sir.
Yeah.
So if you conclude, sir, no problem. Yes, sir. Please conclude it.
I can conclude.
Yeah, no problem, sir. Sir, this is. Can I conclude it, sir?
Yeah. It's up to you. If nobody is there, nobody is asking, it's fine.
Yeah. 1 second.
I can see some people are asking why DC transmission not implemented practically, very less compared to AC transmission.
Yes, sir.
It involves so much of converter systems, right? Only for high power thing they will be used. Is there okay. Any more?
The participants, if you want to ask something regarding the session, can you please raise your hands, or can you post a question? No problem.
Sir, I have a doubt.
Yes.
Yeah, please.
Sir, what is the basic difference between non-isolated DC to DC and isolated DC to DC converter, sir?
In case of an isolated DC-DC converter, your input voltage and the output voltage will not be having the same common ground.
Okay.
Okay.
So
Whereas in case of you take a normal buck converter or a boost converter circuit, you can see the output voltage and negative or and the supply voltage negative are in the same, which is a
Okay.
not thing.
So where we get soft switching easily, sir? If you go for a isolated because of natural zero, it is easy, no, sir?
No, there is no natural zero. Isolated, it doesn't depend on whether it is isolated or non-isolated. See, basically, you are making the current or the voltage, current through the switch or the voltage across the switch to go to a forced zero in case of soft switching. Okay,
sir.
It has nothing to do with isolation or non-isolation. Okay.
Okay. If you go for medium or high power applications, which is recommended, sir? Non-isolated or isolated DC to DC, sir?
Isolated is recommended. If you are going for high power application, yes, isolated is recommended.
Okay. Okay. Thank you, sir.
Yeah. There are a lot of questions in YouTube, I think. See, one thing we can do, there are a lot of questions pouring in the YouTube. I cannot.
Yes, sir. Yes, sir.
Send it to my email.
I will ask you, sir. I will 1 second.
Yeah.
Right now we are having so much of questions. Nowadays we are getting embedded control DC to DC switching device in a single chip. So which is the best one to use, external controlled switch or embedded?
We are getting embedded control DC-DC switching device on a single chip.
Yes, sir.
See, obviously people want to have a high power devices and a very small thing. That is preferable. Like you have an embedded control of DC-DC switch on a chip, single chip itself. Okay. But that will have some limitations. The power limitations may be there. Okay. But if you want to design your own thing, then you need, if a high power application, then it is external controlled is better.
Yes. And one more question, sir. Is there any fundamental difference between modulation of MMC inverter and an MMC rectifier?
Modulation means, does it mean control?
Maybe, sir. Maybe. Is there any fundamental difference between modulation?
No, I don't think there is any difference. It's only in an inverter it converts to DC to AC and then rectifier again AC to DC. That's it. Yeah. Okay. I'm not very familiar with MMC.
Yes.
Yeah.
Why isolated is recommended for high power applications?
See, on the low power side, for example, on the low voltage side, you have some switches. If you want to protect it from a surge, if anything happens on the low power side, or if anything happens on the high power end, that thing should not be coming and affecting your low power or low voltage side. There should be an isolation. Then you are basically protecting the various switches. When you are creating an isolation means you are protecting the circuit.
Yes. Yes, sir. One more question, sir. Please throw some light on T-type converter.
T-type converter. No, I do not exactly understand the question. What is T-type converter?
I don't know. Okay, one more, sir.
No, I think Vijay Krishna, we can do one thing.
Yes, sir. Yes, sir.
I have some specific doubts. Some things I may not directly answer it now because I also have a limitation.
Yes, sir. Yes, sir. Yes, sir.
I did not work on, so I don't give a wrong answer.
Okay.
If they can send it by email, I can do.
Yeah, sure, sir. Sure. Definitely, sir.
Yeah.
So one more question, sir. Dr. Santhan Kumar, can you suggest a DC to DC converter topology for EV powertrain in terms of reliability, cost, and efficiency?
See, again, EV, what is your input? Is it a battery, or is it a fuel cell, or it is from DC-DC convert, or it is from a solar power? Okay. If it is a battery, then you should have a dual bidirectional future. Am I right? because battery has to be charged and discharged. Okay. Or sometimes from the regenerating braking, whatever power is there, that can be again charged back to the battery. Then you need to use a bidirectional DC-DC converter. If it is from a solar power, it is only one direction. Then you can use a normal boost converter or in some ZVS based boost converter or something like that. It depends upon what is your input. Okay.
Yes, sir.
Yeah.
Okay, what is the difference in filtering requirements for DC converters and inverters?
Again, it is application oriented, right? Filter requirement means, see, if you are trying to have an inverter and trying to connect it to the grid, then you may use an LC filter or an LLC filter. There are so many applications. Okay. Whereas in case of a DC-DC converter, the major filter you use is to ensure that from the source you are not drawing a discontinuous current.
Yes, sir.
Okay.
Yes, sir.
Basically to reduce the EMI problem. Then you need to design an LC filter there. Okay.
Yes.
To reduce the EMI problem.
Okay. Where do we use these power converters in 6-phase transmission system?
6-phase, first of all, I'm not very adverse with 6-phase transmission system. So I have to look it into it. Yeah.
Yes. As a difference between L-type and M-type converters?
As I said, L-type and M-type, I'll show you the waveform.
Yes.
Oh, I stopped sharing it, right?
Yes, no problem, sir.
See, each one, for example, application wise, we have different types of quasi-resonant switches. Okay.
Yes, sir.
One is L-type and another is M-type. It depends upon on what application you are actually using. For example, you in case of M-type, that to current mode, the capacitor is placed across the switch. That means the capacitor that is internally having the what we call parasitic capacitance can be directly used in case of an M-type, but the rating should be slightly higher. You need to put an external capacitor there.
Yes, sir.
Okay. If you want more details on these L-type and M, you can see power switching converters by Simon Hang.
Okay.
Okay.
But this is also one of the questions, sir. One of the participants is asking which book is suggested for this one.
See, if you want a very good understanding of DC-DC converters, you can go and look at power applications, converter applications by Professor Nedmohan,
Okay.
and power switching converters by Professor Simon Ang, Simon Ang, A-N-G. Okay. Even Professor L. Umanan's book on power electronics is also very good for these things. Okay.
Yes, sir.
Yeah.
Yes, sir. With this, we sincerely thank you, sir. Really a valuable and informative session.
Thank you.
It's really great session, sir. Thank you, sir, and thank you very much. On behalf of EEE department, I convey my thanks to you, sir. Thank you very much.
Okay. Thank you.
Yes, yes. Thank you, sir. Thank you very much.
Thank you.
Yes, my dear participants, and feedback form and feedback link and attendance feedback and attendance link will be available at our chat boxes, both YouTube and Zoom. Can you please fill it? It will be available up to 8 p.m.
Okay, thank you, sir.
Yes.
Thank you, sir.
Yes, ma'am. Madam? Hello? మేడం చెప్పండి మేడం. అవును మేడం, ఒక మన 2 hours లైవ్లో ఉంటుంది మేడం, ఎందుకంటే ఫీడ్బ్యాక్ లింక్ ఉంది కదా మేడం సెషన్లో. అది పార్టిసిపెంట్స్ లెఫ్ట్ అవ్వచ్చు మేడం, ఇబ్బంది లేదు. ఓకే మేడం, ఫీడ్బ్యాక్ లింక్ ఫిల్ చేయండి, మీకు పెడతాను మేడం, మన గ్రూప్లో కూడా పెడతాను. సరే మేడం, ఓకే మేడం. లేదు మేడం, ప్రిన్సిపల్ గారు వెంటనే లైవ్లోకి వచ్చి స్టార్ట్ చేశారు సార్, ఒక 5 minutes అనే లోపే స్టార్ట్ చేసి చెప్పేసి వెంటనే లెఫ్ట్ అయిపోయారు మేడం. నేను యాక్చువల్గా మనం ఏంటంటే 3:30 స్టార్ట్ చేస్తామన్నట్టు చెప్పాను, 3:30కి జస్ట్ మా సార్ ఇట్లా వచ్చి చెప్పేసి వెళ్ళిపోయారు. అవును మేడం, నేను వీళ్ళందరినీ ఒకేసారి ఈ అకామిడేట్ చేయడం ఇబ్బంది అయిపోతుంది మేడం. ఈ జూమ్లో ఏంటంటే అందరూ వచ్చారు. Yes, sir. Sir, good evening. Yes, sir. Nice session, sir. Really, sir.